thank you very much. Thank you to Khalil for inviting me and giving me this opportunity. The work I'm about to present is the result of joint research with Douglas Gonçalves, Antonio, and Tanguy Migaud. To tell the truth, I'm not a big expert of distance geometry. I mostly relied on Douglas and Antonio on this part, so if I make mistakes, do not hesitate to interrupt and correct. The talk is about the discretization of distance geometry graphs, and actually more generally about a problem that can be defined as discretization of graphs in some dimension k. And I will talk a bit about algorithmic complexity and about the solution methods. Okay, so, well, that's what I just said. Okay, just first, just to fix the ideas, we have a graph that is simple and undirected, and positive integer k. And so a vertex order is basically a bijective function that gives a rank to each of the vertex. And so I will need this term in the rest. It's quite important. So if you have, if you're considering a vertex u that is a neighbor of another vertex v, and that is also a predecessor, such that u is also a predecessor of v in the order, then u will be called a reference of v. Okay, so a reference is basically a neighbor that is also a predecessor. Okay, and so from this we can define a discretization order as being a vertex order such, well, discretization order in dimension k. It is a vertex order such that the first k vertices of the order form a clique, and the remaining vertices will have at least k references. Okay?
What is this -1, sigma inverse of -1?
Well, that's the vertex that has a rank k. That's the inverse. That's the inverse function of, like sigma gives the rank.
Why -1? Is there any vertex that is called -1? There is a minus.
Oh, at the beginning, because that's a typo, basically. Okay. That's one. Okay, that's one. I went too fast correcting this typo.
Cut and paste.
Not even, no.
Missed the -1?
No, I didn't. Obviously not. I don't know. I must have been exhausted. Okay, so basically a discretization order is such that the first k vertices form a clique and other vertices have at least k references. So the problem of determining whether a graph has a discretization order is the discretization vertex ordering problem. And so, well, there is obviously a huge link with a distance geometry problem, as was mentioned in the previous talks, because, well, if a graph admits a discretization order so that the references of each vertex do not belong to a Euclidean space with dimension k-1, then the graph is said to be discretizable, and it could be, and then the problem, the distance geometry problem, can be discretized, meaning that we are going to be able to solve the problem by sequentially assigning positions to the vertices, and so that each time you will have only a finite number of possible positions. Okay, so at this stage, well, this problem, only finding a discretization order can be done quite fast. The thing is that we can identify two different situations. One where a vertex has exactly k references, and one where a vertex has more than k references. The thing is that when the vertex has exactly k references, it can take at most two different positions. Okay? So in this case, we will call the vertex a partially referenced vertex. And when the vertex has more than k references, then it can take at most one position, okay? I'm talking in the context of a branch and prune algorithm, for instance, where we sequentially assign positions. Okay, so, well, clearly every discretization order provides a strategy to enumerate all the possible embeddings for the graph. But each time that you have partially referenced vertices, you may have to, you will get a larger enumeration tree because possibly you will have two possibilities each time. Okay. So this is illustrated there. We have the graph above, like the order, well, it should have been 1, 2, 3 instead of ABC, but basically the alphabetic order gives the discretization order. In this case, what happens is that the initial click, we are in dimension 2. The initial click are the two vertices A and B. And then the vertices C, D, and E will have exactly 2 references each. So they are only partially referenced vertices. Okay? And then, well, possibly the enumeration tree of the branch and prune will look like that, meaning that it will be, well, nearly as large as possible. Okay? The thing is that in this case, it was possible to order the vertices differently. Okay? So that, well, C has only A and B as references. Okay? But D has A, B, and C as references, meaning that it has K plus 1 references. So it's fully referenced, and you have only one possible position. The same holds for E and then for F. Okay? So here, the tree is clearly much more narrow, and we won't have to, well, and the branch and prune, for instance, should run much more efficiently. Okay? So that's the idea here is that, well, each discretization order draws one branch and prune enumeration tree, and the smaller the tree, the faster the enumeration should be. Obviously here, the real contribution of branch and prune is that you can clearly cut the tree at a lot of places using extra distances or other information, so that the exact size of the tree cannot be known before actually enumerating the possibilities. Okay? But, well, at the stage where you're only looking for a discretization order, you don't want to do that, to actually solve the problem. So we only looked at 2 approximations of the problem that consist in, well, having the smallest tree as possible. One where we simply minimize the number of partially referenced vertices, meaning those that have exactly K references. And another one where we minimize the number of nodes in the branch and prune tree without pruning, or before pruning anything. Okay? And mostly I'm going to focus on the first one in this presentation. So we go from feasibility problem, DVOP, the discretization vertex optimization ordering problem, to 2 different optimization problems. Okay. Actually, the discretization problem has other potential applications, which is quite interesting to see. I'm just talking about 2. One that has actually been published, another one that is mostly from my and Antonio's brain. So the first one is scheduling is a particular scheduling with precedence constraints, where you have only one machine, and the jobs have a potentially large number of precedence constraints, but only K among them have to be satisfied. Okay. So in this case, it is exactly the discretization vertex ordering problem that we are solving. We can also look at optimization versions where we maximize some reward for extra precedents that are satisfied. Okay. Then we get kind of the mean partial problem I was talking before. Another thing is, well, an organization of a scientific event where you may have, I don't know, like talks that are more and more targeting experts, okay? You don't want to put the talks that are targeting the experts first, okay? So you may want to say, okay, I'd like to schedule the event so that each participant will be able to attend, I say K, talks related to each presentation before attending a given presentation, okay? And we can also have an optimization version that is going to be exactly equivalent to a mean partial problem. We will also give a reward if K+1 talks can be attended before attending another presentation. All right. So these are two possible. There are quite a lot more, actually. And also we can see that I'm thinking about the talk, the tutorial this morning. We may also see mean partial as the problem that that is going to find how far is the instance from a globally rigid graph. I guess something like that. Not sure, but maybe I'll have a confirmation later. Okay, so sorry. First, I'm going to give some results about the algorithmic complexity of these two problems. And I'm starting with just a look on, well, small look on the state of the art. So the feasibility problem is NP complete if the dimension is allowed to vary, okay? Because a discretization order starts with a click, so you already have to find a K click. Then if K is fixed, then the problem can be solved by a polynomial greedy algorithm that was given by Khalil and Cotter, I guess also Leo, and in 2012, where you look at each click, and then you assign, you add to the order, you sequentially add to the order the vertex that has the largest number of references among the vertices that are not ordered yet, okay? And then you know that if the vertex that has the biggest number, or the largest number of references has less than K references, then you won't go to a discretization order from this click, so you go to the next click. And well, in the end, you necessarily get a discretization order if there is one, okay? One last result is when when there must be at least K references that are contiguous and direct predecessors of each vertex. In that case, even if K is fixed, the problem remains NP complete. Okay, so well, K being fixed doesn't mean that it's necessarily going to be easy. Okay, so from the literature, what we immediately deduce is that the problem is, the optimization versions of the problem are going to be NP hard if K is allowed to vary, but that's not really what's interesting in general because, well, in our case, because K is the dimension where we search for an embedding, so it's usually small, 2 or 3. So basically, we have to figure what's happening when K is fixed. So I'm directly giving the results, and I won't go a lot in detail. I won't detail a lot the proofs, not even at all. Okay, so it appeared that the two problems are NP complete, and it's true as soon as K is greater or equal to 1. Okay, so it's always NP complete. When K, even if K is fixed. And that's true for the two problems. So basically, well, that's a bad news from the point of view of DGP because that's only a pre-solved phase. So maybe we don't want to do that, but still I got interested in the problem, so I dug up. And just one word about the proofs of NP completeness, of NP roundness. So what you do usually, for those who are not familiar, is that you go from, you take a problem that you know is NP hard, and you show that you can solve it by solving the problem that you are studying by transforming the first problem into the one you're studying through a polynomial transformation. Okay, so actually, if k is greater or equal to 3, that's the first proof we found, and it took a lot of time to find the general case, actually. There is a reduction from mean vertex cover. Mean vertex cover, well, vertex cover is the problem of finding the smallest vertex cover in a graph. A vertex cover being a set of vertices such that every edge has one of its extremities in this set. Okay, so this is one of the first problem that was shown to be NP complete, and actually it appears that it's even NP complete if the graph has bounded degree, vertices degree, and if this bound is equal or larger to 3. So as soon as the bound is 3, it's already NP complete. So you can have really like graphs with only a few edges, and it's already NP complete. So basically, that's why we have only k equal or greater or equal to 3 here. That's because when we do the reduction, k is going to be the maximum vertex degree of the vertex cover instance. Okay, so that's the link. And that's why we couldn't do better the first time, because as soon as you go to 2, you go to a matching problem, this polynomial. So for k equal 1 or 2, the proof had to be by polynomial reduction from 3-sat, which is one of the, well, it's usually technical. There's a lot of gadgets and things. It takes 5 pages to prove the thing. And then, well, the second problem, mean node, is then proved to be NP-hard by polynomial transformation of the first one. Okay, so this wasn't that hard. Okay. So, but, well, the problem being NP complete, the first reflex was to go to integer programming approaches, like just looking what the commercial solvers can do with this problem. And so we characterize an order by precedence variables. So for each pair of vertices, u and v, you have one binary variable, xuv, that says whether u is before v or not, okay? And so you need to do 2 things with this order. One is that you need to ensure that the precedence variables are actually going to describe a total order, okay? They can just describe something that is just precedence that have no sense, actually, okay? And the other one is to make sure that the vertex is a discretization order. Okay. So actually, this led to 3 different formulations that will behave differently, the 3 of them. We also develop IP formulations for the second problem, but well, it's still a work in progress. We haven't done a lot of tests, so it's not useful to talk about it right now. Okay, so first, the discretization constraint. So we need extra binary variables indicating for each vertex if it's fully referenced or not. And also one variable per k-click, which states whether the k-click is the initial click of the order or not, okay? And then, well, you say that you need to take at least a click, and you say that a vertex that does not belong to the initial click must have k references, and it is fully referenced only if it has more than k references. Okay. So we get a formulation with only, well, this takes only a few constraints, so the problem remains compact and quite small. The model remains compact and quite small. But to impose the total order relation, what we can do just like by looking at just the definition of what is a total order. You need that for each pair of vertices, U and V, you need that XUV says that either U is before V or V is before U. And you need to say that for each triplet, U, V, W, if U is before V and V is before W, then U is before W. And then you're sure to have a total order. Okay? So the problem here is that those transitivity constraints are in a cubic number. So here the model might be quite large even for a medium size instance. Okay. And then, in the problem, you just minimize the number of partially referenced vertices. Okay. So another formulation was a bit more like the Miller-Tucker and Zemlin formulation of the traveling salesman problem, where you add variables just giving the rank of each vertex. And then you say that if U is before V, then the rank of U must be smaller than the rank of V. Okay? But there is that kind of big M that is the cardinality of V here. So you get a lot less constraints, but basically the linear relaxation of the problem can be much less informative, okay? And a lot weaker, actually. So we still went to another formulation, like after a preliminary test. Clearly, those two were not satisfactory. So we also looked at another interpretation of those precedence constraints. You can see those precedence variables. You can see the XUV as an indicator of as giving an orientation to the graph. Meaning, if XUV is equal to 1, then you take an arc instead of the edge, and the arc goes from U to V. Okay. So basically, what you want to have a total order is that the variables XUV define an acyclic orientation of the graph. Okay. And for that, you can express that by just forbidding every cycle of the graph. So obviously, you get a potential number of constraints, which is exponential. So we added them iteratively in a cutting plane procedure where you solve it with no cycle. Then every time you find a cycle, you add the constraint until you get a constraint, until you get a solution without cycle. Okay. All right. So we compared the three formulations on an instance, on a benchmark of instances generated from 19 geometries from the protein data bank. We only kept, in these geometries, we only kept the distances smaller than 6 angstrom, and the dimension is 3 in every test. Okay. So what we wanted here is to have instances with different sizes, different number of vertices, different number of edges, and we are not interested in having instances that are infeasible, because actually it's polynomial to show that it's infeasible here, so there's no interest. So we first ran the greedy algorithm to get a discretization order of the instance, and then when we want only a small number of vertices, we keep only the first vertices of the discretization order. Okay. And likewise, when we want to reduce the number of edges, we only remove edges that do not prevent the order from being a discretization order. Okay, so we only keep instances that are feasible. And then we compare the formulations for a different number of vertices, and we look only at the best formulation for a different number of edges. All our tests are with the commercial solver iLog-Cplex, and with the 1,000-second time limits. So it's really long compared to the times that were shown this morning to actually solve the instance. But, well. Okay, so, well, very bad news. That's the number of solutions solved to, of instances solved to optimalities when the number of vertices increases. And, well, clearly, the problem is not able to solve them all to optimality as soon as there are 40 vertices. And, well, the first two formulations, the two compact formulations with transitivity constraints and ranks constraints, like fail to solve any instance starting from 70 vertices. Okay, so clearly the problem is hard to solve with IP with integer programming approaches. Okay, we observe the same thing for the relative duality gap at the end of the time limit for the instances that are not solved to optimality. Okay, just one informative slide, a graph. Here I look at the average solution time of the linear relaxation, and clearly the fact that the first model has a lot of constraints make that it is a lot longer to solve it, to solve just the linear relaxation. Okay. And well, that's it basically. Okay, what I was looking at here is the evolution of the solution time of the best formulation, meaning the one with cutting plane generation, when the number of edges varies. Okay, this is that's in person. That's a bit odd, but actually this is there you have 3.1 edges per vertex, and there you have 5 edges per vertex. Okay, so clearly where it is the most difficult, here you have the average relative gap. Here you have the number of solutions solved to optimality. Where it is the hardest is when you have approximately k plus 1 edges per vertex. So that's expected. Actually, that's where you have most choices to make. If you have exactly about k vertices edges per vertex, this means that you only have actually one discretization order, and that every vertex in this discretization order has exactly k references. So the solution is trivial, and that's why it's always easy to solve them. Okay? When you have a lot of edges per vertex, actually it will be very easy to find the best possible solution. That's why it's easier there, but even if there's still difficulties. And that's in the middle that you have most difficulties. Okay. All right, so one big conclusion by that, clearly integer programming approaches are not fit for the problem, or you will need like really smarter things. I don't know, maybe if it's possible you can do some decomposition when you're able to observe some globally rigid substructures and do things like that. So maybe that's a possibility, but like naively, that's not an option. Okay, one other thing that we found that did not appear in the graph is that actually the greedy algorithm alone was always run to give an upper bound to the commercial solver from the beginning. And it appeared that when we were able to find an optimal solution, we were able to see that the greedy algorithm always finds an optimal or near to optimality solutions in our test, okay, on these instances. Well, that's protein instances, so maybe, well, there's a logic to it, like the greedy algorithm does the right thing usually. But, well, here it's interesting to see that. So, well, clearly the bad quality of the duality gap are only due to the bad quality of the linear relaxations of the models. So here we might be more interested in a purely enumerative approach, where we don't use linear relaxation since it doesn't give any valuable information. Okay. That's why we developed a specific branch and bound algorithm. How much time do I have?
3 minutes.
Oh, that's what I have left?
Yeah.
Okay.
And then 5 minutes reflection.
Okay, so I'm just not going to say a lot about it, but basically what we say is that the greedy algorithm only makes an impacting choice when the vertices that has the largest number of references all have exactly k references. That's the only moment when the greedy algorithm makes a real choice. Okay, all the other choices do not impact the value of the solution it returns. So the branch and bound we designed will enumerate the discretization orders produced by the greedy algorithm by creating, by branching every time you have this kind of choice to make. Okay. And then we used, well, we computed upper bounds just by using the greedy or updating it when we reach a leaf of the branch and bound. And the lower bounds were just computed from, well, logic. If you have a vertex, an unordered vertex that has exactly k neighbors, then it will necessarily be partially referenced. So you can update the lower bound like this. And we also use some dominance rules to prune the tree a bit more. Okay, so well, since I don't have any time, I'm just going to the results. It has been quite interesting to see that in red you have the results of the branch and bound. Here we actually vary the vertices and the edges. And what happens here is that we see that the branch and bound is able to find optimal solutions even for the largest instances that we looked at. And what is interesting is that when it fails, it's only for the instances that have only a small number, about k edges per vertex, which is also the case where the integer programming approaches behave best, well, where they are most efficient. So interestingly, like the two things could be used in complementary with complementarity. So basically, that's the that's the message here. And also, when it finds an optimal solution, it usually goes very fast to do so. Okay. So so here maybe the branch and bound could be used as a pre-processing phase. I mean, it takes nearly no time when you have a good instance. Okay, and then I just compare the two optimization problems, and we saw that the two can be solved quite well. The solution times and number of optimal solutions found are quite similar in the two cases. So the two problems are just as difficult. Okay, and well, that was the message. Maybe like just telling that well, the problem is still our work is still in progress. We don't have published the work on the branch and bound. So well, I'm sure we will find some improvement, well, even many. And also we are quite impatient to go to larger experiments, like looking at other kinds of instances from other applications to see really what's up. Okay, so that's it.
Are there any questions?
Yes. Good talk. Congratulations. But the number of constraints is polynomial, but the number of variables is polynomial solved or exponential?
No, the number. You mean in the first formula? In every formulation, it's polynomial and it's small. It's either the number of variables squared or the number of edges, plus one per k click. But well, it's going to be a polynomial with k as in exponents. K is supposed to be fixed and small, actually.
Okay, but the same way I have some recommendations for you. For example, integer programming, branch and bound is a kind of integer programming. Is integer programming also?
Yeah,
If you apply simplex, you apply a branch and cut.
yeah, clearly.
Is more powerful than the branch and bound. The problem is your formulation, and probably do you check the effectiveness of the cut inside the branch and cut, the branch and cut of the
Yes, I looked into that. I did a lot of tests, changing the cuts, doing a lot of things like that. I didn't talk about it here because I didn't think it was like...
that should find some cuts and
The thing is that clearly first it just wastes a lot of time solving the relaxation. Every time it solves the relaxation, it wastes time. Because I didn't talk about it, it was written in the slide, but I compared the bounds that I was able to produce myself with the result of the linear relaxations, all of them. And it's always best to just have more naive arguments to find a lower bound, then solve, you get a better lower bound, and obviously it takes no time. So you're just better with that. Clearly, the impact of the cuts is always a bit dark, in particular with simplex, so I tried to deactivate things and such, but well, it was never useful. I never got anything useful. The formulations, well then, it's quite classical, and there's a lot of literature about formulations for linear ordering, obviously for TSP, and all these things I reviewed quite profoundly. This part is actually published, and I took my time on this. So there might be a better one. I would be very curious to see if there was one that was really efficient.
Another possibility to try constraints programming.
Yeah, well, clearly. Yeah, no, totally. Clearly that's... Yeah, clearly. Constraint programming should be better. Much like in the case of scheduling, where a lot of problems are much more efficiently solved with constraint programming than with integer programming, well, meaning branch and cut with relaxation and stuff. Yeah, I do agree on that, definitely.
All right, thank you, Steve.